Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Can a discarded plastic bottle be transformed into textile yarn traveling faster than a high-speed train? Surprisingly, yes. Industrial recycled PET spinning systems can wind yarn at speeds of up to 3,500 meters per minute, that is 210 kilometers per hour. Some modern polyester processes operate beyond 5,000 meters per minute. A bottle that once carried drinking water can eventually become a sports jersey, carpet, jacket, or industrial fabric. But how does a rigid plastic bottle become a soft, flexible thread? Let us enter the engineering world of high-speed spinning. Most transparent beverage bottles are made from polyethylene terephthalate, commonly called PET. Chemically, PET bottles and polyester textile fibres belong to the same polymer family. The transformation begins when compressed bales of used bottles arrive at the recycling plant. These bales contain PET bottles, but also caps, labels, adhesives, metals, PVC, and other plastics. First, a bale breaker separates the compressed bottles. High-speed near-infrared sensors identify plastics according to light reflection. Air jets then eject colored PET and PVC containers. The bottles are shredded into flakes the size of a fingernail. These flakes enter a float sink tank. PET has a density of approximately 1.38 grams per cubic centimeter, so it sinks. Bottle caps made from polypropylene are lighter than water and float. This simple density difference performs a critical separation. The PET flakes pass through hot washing, friction washing, and multiple rinsing stages. Heat and controlled alkaline cleaning remove sugar, oils, glue, and label residue. Mechanical friction scrubs contamination from the flake surfaces. The flakes are then centrifugally dried and inspected again for quality. PET is hygroscopic, it absorbs moisture. If wet PET enters an extruder, water attacks its molecular chains at high temperature. This reaction, called hydrolysis, reduces molecular weight and weakens the final yarn. The flakes must be dried until moisture is nearly zero. Recycling and repeated heating may reduce PET's chain length. Engineers measure this through intrinsic viscosity, or IV. Higher and more stable IV generally indicates longer polymer chains and better melt strength. Solid-state or liquid-state polycondensation can rebuild these chains, removing volatile compounds and spinning oils. The clean, dry PET enters the extruder. A rotating screw transports, compresses, and melts the material at temperatures typically around 280 degrees Celsius. The molten PET then passes through fine filtration systems to capture any remaining microscopic particles. A gear-type metering pump delivers an extremely accurate and nearly pulse-free flow. The purified PET melt reaches the heart of the plant, the spin pack. Each microscopic spinneret hole forms one continuous molten filament. As the filaments leave, carefully conditioned quench-air rapidly and uniformly solidifies the polymer. Next comes drawing. The yarn passes over Godet rollers operating at different speeds. Stretching the yarn aligns the tangled PET molecules, dramatically improving strength, stiffness, and dimensional stability. This process determines if the yarn is POY, FDY, staple fiber, or higher tenacity industrial yarn. The yarn now enters the high-speed winder. Modern recycled PET compact lines can produce more than 17 tons per day from one line. Heat, drawing, and false twisting create microscopic curls called crimp. These curls give polyester fabric softness, stretch, and better thermal insulation. Finally, automatic changes transfer the running yarn without stopping production. A high-speed spinning plant is controlled by an integrated network of sensors. The system continuously monitors melt temperature, pressure, yarn tension, and winding speed. At 3,500 meters per minute, a yarn break develops too quickly for manual reaction. Sensors must identify the fault and warn operators within seconds. Producing polyester from recovered PET reduces the demand for new fossil-based raw materials and prevents useful polymer from immediately entering landfills or incinerators. Oerlikon reports that substituting rPET for virgin PET can reduce the fiber's carbon footprint by more than 70%, although future plants must move toward textile-to-textile recycling to truly close the loop. A recycled polyester thread may appear simple, but behind it lies an extraordinary combination of polymer chemistry, thermal engineering, and digital automation. A bottle is sorted, washed, melted, and forced through microscopic openings. Its molecules are stretched into alignment, giving the bottle an entirely new life.